For this lesson, we're going to take what we've been discussing about rates of change and we're going to apply it to graphical models. So, in other words, taking a look at the graph of the rate of change and comparing that to the graph of the function itself. Now, the thing that I want you to keep in mind throughout all of this, and it's something I've been stressing since we started discussing rate of change, oh, that didn't work very well, which is that rate of change has to do with the slope. So you need to keep that in mind. At its basis or at its core, rate of change is just a discussion of the property that you are already familiar with. The difficulty now, the difficulty with this current lesson is going to be keeping straight whether or not you're talking about the function, in which case we're talking about the slope of the function, and the fact that the slope of the function, the slope of f at x or whatever your function happens to be, corresponds to some other description for your rate of change. I've drawn here three of the most typical descriptions that you're going to have for these. And it's up to you how you want to look at these. I can't even decide myself which way I should represent these to you. So it's up to you whatever you want to look at. But in this case, I'm actually describing the rate of change first, but you need to understand these descriptions could be reversed. So in this case, it says I have a positive rate of change. So that means that the rate of change is a positive number, and that means the positive slope is the slope in the function f of x. It's not saying that the rate of change has a positive slope. It's saying that the function itself has a positive slope. So here, this is what a positive slope looks like, and so this is a positive number. For a negative rate of change, and once again, this slope is in f of x, and this slope is in f of x. So for a negative rate of change, here's a negative number. In the function itself, here's a negative slope. So that means that a positive slope, the function is increasing. A negative slope, that means the function is decreasing. And then if we have no rate of change, if the function is not changing at all, that means the function is constant. And the rate of change, what does it mean to have no rate of change? That would mean the rate of change is equal to 0. This is a particularly confusing one because, as you can see, the rate of change here is 0 and a horizontal line. The rate of change here, the slope here is 0, but it's not necessarily going to be along the x-axis. As is unfortunately the case in so many concepts in mathematics, you just need to work with these things, you need to practice them and make them your own. The only way to do that is through practice. Okay, so we're going to do some exercises now. I've described a bunch of situations, and in those situations I'm either describing the function or I'm describing the rate of change. So let's take a look at what we have here. The first one says that the function is increasing at a constant rate. So first of all, the function increasing, what does an increasing function look like? That's an increasing function, that's an increasing function, that's an increasing function. It's something that in some way is going up to the right. But in this case, we're being told that it is increasing at a constant rate, which means it's going to be going up to the right along a straight line. So I'm just going to go ahead. I'm going to start my function at 0, 0, and I'm going to do that consistently throughout these exercises. So the one thing, here's just a bit of advice. Don't start your function too steeply or too shallow. Better to actually go shallow rather than too steep, because steep doesn't give you a lot of room to work with, and you probably might guess the best thing to do is just to choose something in the middle. So I'm going to choose something here. It's arbitrary, but this function is increasing at a constant rate. Then the function stays constant, so that would mean that the function is not changing for a while. Then the function is decreasing at a constant rate. Now, decreasing at a constant rate might mean that it's decreasing in a very shallow way. It might mean that it decreases in about the same way that it did before. It might mean that it decreases very steeply but still ends up back at x equals 0. and basically anything below the horizontal is valid. So I could go here, I could go here, here. So I'm going to put a steeper line, and I'm going to show you that it's okay if it finishes below the x-axis. Now, what does this mean for rate of change? So ask yourself, what is the slope? In this case, we're given information about the function first. So what is the slope here? In this case, that is a slope that's positive, but this is a straight line, which means the slope is positive and constant. So my rate of change is going to be positive and constant. So that first section is going to have a rate of change that looks like this. A positive slope, but constant. I'm just going to put that in here just to remind you, which is the rate of change is the slope. So we ask ourselves about the slope of f of x. We ask ourselves questions, or we answer questions about the slope of f of x, and we relate that back here. Then we're told that the slope of f of x is constant, and that is a straight line. Now, unfortunately, with my straight line tool, I believe this is not going to show up very well. So I'm just going to put it a little bit above. That shows up okay. I guess you can see that there. Might be better if I change the color of these. So let's change that line over to be blue and change. We don't really need to change this one. Okay? And then finally, it says it is now decreasing at a constant rate. So that is well, what kind of slope is that? That's a negative slope, and constant rate means it's staying the same. So here I had slope greater than 0. Here I've got a slope equal to 0. Here I have a slope less than 0. So how do I get a slope less than 0? And that's going to be down here. It's more steep than the positive slope. So I'm going to try. I'm not doing this with a very accurate scale, but I'm going to put a little bit of effort into making it look reasonable. Okay, and so there we go. If you like, if you prefer visually, you can connect these with some dotted lines to show that transition. So this is the positive slope, this is the zero slope, and this one is the negative slope. The rate of change is constant and negative, then constant and positive, then zero. This next example starts by talking about the rate of change. The rate of change is constant and negative. That brings me over here. I'm just going to freehand this in this time, see if I do a reasonable job. I don't particularly like that line tool because of the limits on the colors. So it is constant and negative. So it's a horizontal line. That's a negative value. Then it is constant and positive. So that means it's now up here somewhere. And it's a horizontal line that's positive. And then it is 0. So that would bring it here. And again, I'm just going to go ahead and dot those in. If you can be neat enough, that's fine to freehand it. To be honest with you, if I could just use a hand ruler here on the tablet while I'm doing this, that would be even better. But this is acceptable, I think. So now I'm going to start here at 0, 0. Let's try to piece this together. This means the rate of change started at constant and negative. This means my slope is negative. My slope is less than 0. So what does a negative slope look like over here? That's going to be, and it's constant, so that's going to be a straight diagonal line down to the right, a negative slope. Then it changes over to positive. So I'm going to put in, now it just so happens, it looks like my negative is slightly bigger than my positive. So I'm just going to make this a little more shallow. And then I have a constant slope of 0. A 0 here. A 0 rate of change means a 0 slope over here. So that's going to be a horizontal line. And there you have it. There are a number of interpretations you could have made to this. This could have been steeper.
and then maybe this one was steep, or was not quite as steep, but went on for a longer amount of time and then went horizontal. Both the red and the blue, technically, because we don't have any scale in here, we can't be too picky about what these things mean. So there's a lot of room for interpretation. But the overall shape here, you can see it's got a negative slope, a positive slope, zero slope. And that's the important part here. And finally, we have a rate of change which is increasingly positive. It's not just the rate of change is positive this time. Now we're saying the rate of change is increasingly positive. Then the rate of change is constant and negative. Then it is decreasingly positive. Now we really need to puzzle out what we mean here by increasingly positive. Now I mentioned that normally I didn't mention, I've shown you this. Normally our rate of change, for example, if I just told you the rate of change was positive, you shouldn't, it's not always going to be the case, but it's pretty reasonable to have just said something like this, which is it's positive, and so it's positive but constant. But this is not constant. It's specifically telling you it's not constant. So it can't be this. It is increasingly positive. That means that the positive value is getting larger. Now I'm still going to make that a straight line. So now it's increasing along a straight line. Let's see if I can do a slightly better job of that. So it is increasingly positive. Then it is constant and negative. So the way that I do that is I bring it down here to the negative, constant and negative for a horizontal line, and then decreasingly positive. And again, this is a tough one altogether. Decreasingly positive, what do I mean there? Well, first of all, I mean it's positive. So then I have to bring this back. I don't have to bring this back to the same level it was at before. I can bring it higher. I can start it lower. It's up to me. It's arbitrary. But so I'm just going to bring it here just to show they don't have to be at the exact same height. And then it is decreasingly positive. So it's always positive, but it's getting smaller. So that means that I end up with something like that. Now this is certainly very different than what we've looked at so far. So let's see, how do we turn this into the function? Now, rate of change, just to remind you again, the rate of change is the slope of the function f of x. Well, if this is the slope of f of x, what is the slope here? It's positive. What is the slope here? Well, it's also positive, but it's now a bigger number. So what does it mean for the slope to be? For example, here, this is positive but a small number. What does a small positive slope look like? That would be a shallow line up to the right. And so let's say that's the tangent through that point. What would the slope look like at a later x value where it's positive but larger? Well, that would be a steep line, and if that's the tangent point. Well, what kind of graphing shape takes me from a remember, tangent means that at this point it's going to look like that, and at this point it's going to look like that. So it has to get there by passing through some sort of curve. So that means here my slope is small as positive, here my slope is large and positive. To go from here to here, it has to pass through all of the slopes in between. And so that means the curve, f of x, is going to look something like what I've drawn here. So I will start again at 0, 0, and I'm going to draw a smooth curve where the slope is increasing. I mentioned in a previous example, watch out, you don't get too steep. Same thing is true here. If you took this too far, you'd very rapidly start to approach a vertical line, and that might limit your ability to deal with some of the other parts of this rate of change graph. So try to keep what you're doing fairly moderate, or just be prepared to erase it and go back and try something new. Okay, now what do we have here? We have a negative slope, and it's constant. Well, what does it look like to have a negative slope? That's a line like this, and it's constant means this slope never changes. So there we go, straight line down to the right.
I went through the x-axis. That was completely arbitrary. I just made a smooth straight line there. Then we go back to having a positive slope. So from here to here, we have a positive slope, but it's getting smaller. So here, my slope was positive and my slope was increasing. Here, my slope was negative. Sorry, I was about to write 0. It's not 0. Here, my slope is negative and my slope is decreasing. I want to go back to positive again. Well, positive slope looks like that, but it's a decreasing slope, which means it might start looking like this, but it has to end still positive, but maybe more shallow. So that's going to be a curve that's going to be going the other way from this one. So this one is slope positive again, but this time the slope is decreasing. It is decreasingly positive. So from here, I can now draw a curve the other way. I could do a better job than that. Okay, there we go. That's a better version of it. So you can see this one is curving upwards. It's getting more steep, negative and constant. This one is curving, you could say this is curving downwards, but it's actually not it's not never decreasing. It's still, the function itself is always increasing here. So that can be a very challenging one for people to deal with. Okay, now a slightly more practical example, just to get you visualizing things, etc. So it tells us that water flows at a constant rate from a tap to fill a beaker, a cylinder, and a flask. Actually, well, I've got a beaker, a flask, it says Erlenmeyer flask, and a measuring cylinder. Draw a rate of change in the water level. And this is very important. It's in the water level. We're not looking at the rate of change of water, the water volume, because we're filling them at the same water volume rate. It's a constant rate from the tap. But if you take a very close look at the pictures that I've got here, each of these actually has 100 milliliters marked on it. But if you look at the height, if we actually measure h of t, which is the height that we read, how high is the water along the side of the container, the beaker is at a medium height, the flask at this point is actually a little bit below, and the cylinder is higher than both of them. Now, why would that be the case? All of them measure 100. And the reason is because of the way that each of the geometries of these containers spreads out the water. So a beaker is a cylinder. The cylinder and the beaker are basically the same shape. The difference is the beaker is wider than the cylinder. So when you start filling this up, every time you put in 10 milliliters, it's going to fill that much. That much height is going to get consumed. But in the case of the cylinder, when you put in 10 milliliters, it goes up higher each 10. And the reason for that is because the cylinder is narrower. So because it's narrower, the water doesn't spread out as much. Instead, it piles up more. And then finally, the flask. The flask is quite wide at the bottom. So when you put in your first measurement, it's actually not going to make much of an impact on the water level. But the more you fill it, the narrower the Erlenmeyer flask is. So then it's actually going to fill up faster and faster and faster. So how can we take what I just described there, how can we turn that into a rate of change or just a graph of h versus t? Now technically, if you understand this, whatever you're comfortable with, you could start with the rate of change, you could start with h as a function of time. I think I'm going to start with rate of change. So if we take a look at the beaker is uniform, and I'm going to ignore some of the little nitpicking features here. For example, the roundness in the bottom corners and the little pouring spout at the top. When I first looked at this, my intention was to talk about these little things, but I think they distract from it. So let's treat the beaker as if it's a perfect cylinder with perfect corners. And so what can you tell me, or what do you think will happen as I fill this? Every tick on the clock is going to change the height by the same amount because it's regular. So in this one, the rate of change is going to be constant. So in this case, my rate of change is constant. I'm going to skip over here to the cylinder just for our discussion. What would you say about the rate of change here? Well, it's narrower, which means the rate of change is going to be faster than it was in the beaker. So my rate of change is greater than the beaker. But otherwise, the rate of change is constant because, again, it's a perfect, from the side, it's a perfectly rectangular shape. Now, what about this one? What can you say about the rate of change of this one? Well, the first thing I think we can say is it's not constant because this shape, although this is a regular shape, it's not always going to be the same. The cross section is going to be changing. It's getting narrower. The narrower the shape, the faster it will fill. So the rate of change of this one is actually increasing. The speed at which we measure, and it's the rate of change in height. The speed that we see the height going up here actually is going to start quite slowly, and it's going to get faster and faster and faster. By the time it gets up here to the neck is actually narrower than a cylinder. So it will end higher than the cylinder. So now let's go ahead and try to put that into application. So the beaker has a constant rate of change. And I think for this one I'm drawing slightly longer lines. I'm just going to go back. And I'm going to choose a modest value for that. So the beaker is going to have a constant rate of change. And once again, just to emphasize this is the rate of change of the function of the height that we read. This is not rate of change of volume. This is the rate of change of the height that we read. Now, what did we say about the flask, which is the one here in the middle? The flask, the rate of change is increasing. Actually, you know what? Let's skip over. Let's go over to the cylinder. What can we say about the rate of change of the cylinder? It was also constant, but it's going to be more than the beaker. And then finally, the rate of change of the flask, it was increasing. It's actually, if we go back again, take a final look, it's wider than the beaker to start. So it's going to be slower than the beaker to start, but it's narrower than the cylinder to end. So it's actually going to go past, so it's going to start lower than the beaker. So I'll start it here. And it's going to rise higher than the cylinder. Hopefully you can see that that's what I've done here. And then an interesting thing that happens right here on the end is it goes constant. So the rate of change is actually not increasing the whole time. The rate of change will flatten out just here at the top. Let's line that up a little more nicely. There we go. So it starts lower than the beaker, it passes the cylinder, and then it goes flat just at the neck of the flask. Okay, can we turn these into something meaningful with regards to the height? And I think, again, I'll use my straight line tool for most of these. So the rate of change here is constant and positive. That means the slope here is constant and positive. The height starts at 0 and increases to whatever the height of the beaker is. The cylinder is the next one that's easy to do. The height of the cylinder, well, the rate of change of height, or the slope of the height, is going to be larger. So this one's actually going to look more like that. And the cylinder is also taller, so that makes sense. And then finally, the flask, which is the most complicated of them, the flask is actually going to start filling quite slowly, and then it's going to be filling faster and faster and faster, and then eventually it will form a straight line, and that's tough. This is very tough to freehand, I will admit. So let's see what I can do here. Okay, that's not bad. It starts off pretty shallow, and then it speeds up, speeds up, speeds up. It's filling faster and faster, and then at the top here is when it takes on the appearance of just a straight line. And again, I'm just going to line that up a little bit better. Okay, so this straight part where the slope is constant, here the slope is constant. Okay, I hope that made sense. Anytime we're dealing with rate of change where the rate of change is not just something simple like constant positive, constant negative, or constant zero, this can get quite complicated. And then when you tack other things on there, there's more to deal with. You're going to need to take some time to practice this and get your head wrapped around it. Okay, that's it for this lesson. Just a little side note, the assigned work here, really, page 103 is the stuff that is related to these graphs, and then the work on page 111, that's really just some extra practice that covers many of the concepts that we've been going over so far in this unit. And that's it for the lesson.